Welcome everybody. I think we're going to wait a couple minutes as folks come through into the lobby, but really excited to talk to you all today. I think we're going to start with some quick introductions. So my name is Dat. I am a solutions architect here at Arize. I build with a lot of our customers kind of at the ground level in the kind of LLM space. So really excited to show you kind of what we have today and what we're presenting on Mistral and Mixtral. And I'll go ahead and let our other presenters introduce themselves.
Yeah, hey, happy to go next. Hey, everyone. My name's Aman. I'm a group product manager at Arize. Been at the company for a couple of years. These days, I'm mostly focused on our LLM product line and helping kind of understand what are data scientists and LLM application builders doing in the space and sort of translating that back into our product roadmap, working very closely with Aparna here, who I'll let go introduce next.
Awesome. And hey, everyone, thanks so much for joining. I think today is going to be a really fun discussion. We're going to go into, okay, we actually, started off thinking we're going to do both Mixtral and Gemini, but as we were putting together the material, we realized we might only have time to get through Mixtral today. So we'll focus on Mixtral, and maybe the next one we'll do Gemini. But yeah, my name's Aparna, run product here, work with a lot of people who are actually putting this stuff out into the real world. So there's a lot of good nuggets I think we're going to learn from this, and hopefully we see more of Mixtral users out there in the next couple months.
Awesome.
Yeah, I guess given how much we got to cover, you want to just hop in and we'll just jump in.
Yeah, really excited. And so let's go ahead and hop in. So for today's presentation, I'm going to go through a little bit of the agenda. I think there's a lot of context knowledge that we want to understand and really give you all to really understand how we got here. How did we get to such a great open source model with Mistral and Mixtral? So we'll definitely cover some concepts like power laws in large language models, what that means, those relationships, and how maybe researchers and people who train large language models are thinking in the space. And so we'll definitely go through a journey of like what was built before Mistral and Mixtral, and then how LLMs got better. And then after that, we'll definitely talk about the recent improvements in these kind of architectures in these OSS models and how they're getting better, specifically in Mistral and Mixtral. And we'll also go pretty deeply into the mechanics of not only dense model architectures, but mixture of experts architectures. So that's today's agenda, and let's get started. And so the first thing to understand is that there's a relationship between kind of three things when you can think training or prepping LLMs for real world applications and performance. The first one you can think is that we're heavily gated on is compute available, right? So you can think we don't have unlimited amounts of compute, and so that's generally the thing that gates us. And kind of based off that, we can really kind of affect or change the next two items. So I'm sure we're familiar all with model size. A lot of how this is determined is parameter size. So if you hear like words like Llama 70B, the 70B is the kind of model size, or 70 billion parameters. Essentially, is how we kind of measure what are the kind of moving, you can think, the changing switches inside of a specific model. So I think most people are familiar with that. And the last important thing too is training data. When we're training LLMs, the relationship between maybe model size and training data is something really important to understand. And so let's kind of travel back in time a little bit by, we can think the good old days in 2020 when OpenAI released this paper, Scaling Laws for Neural Language Models. The TLDR on this paper right here is that OpenAI essentially wanted to answer a question. And the question was really, given a certain quantity of compute, how large of a model should I train in order to get the best performance possible? And what should the data associated with that look like? So essentially, how do I create the most performant model based off of a specific compute constraint? And so the main takeaway I want you to take from this, and so we can look at basically this kind of one image, essentially kind of summarizes their findings. So as you can think model size kind of grows and data size kind of grows, the relationship they tended to understand was that, model size is almost has the most kind of effect on performance. And so we can run through some napkin math, but for this figure here, what essentially they found was like for to optimize compute efficiency when training, they said that, hey, most of the increases should go towards increasing the model size, aka the parameters. A relatively small size in the increase of data is needed to avoid reuse of said data. So they're basically saying, hey, it's more important to have bigger models and less data. There's some napkin math is.
That would you say, we had a question from someone in the community asking, is model size a function of just n parameters as well as number of layers, or how do you define it here as you're talking about this?
Yeah, that's a great question. In dense models, we tend to think of model size as what are the number of, you can think neurons, or how many parameters are being, you can think fired you can think inference time. And so the answer to that question is, yeah, it's like in dense models, we can think of that as parameter size because all neurons are being used. We'll talk a little bit later about MoE and what that looks like, what is sparseness, things like that. But for the most part, in this case, in the early days, it was definitely model size. And so, great question. And so TLDR, if we do a little napkin math, if I give you 10x more compute, according to this paper, you should increase your model size by about 5 and your data size about 2x. If I give you another 10 after that, right, the model size increases by 25 and the data only 4. So you can start to see this kind of power law kind of form. And so the result of this paper in early 2020 was that researchers really took this to heart, and everybody was like, "Oh, OpenAI is doing really well." They really focused on creating larger models, and that's why in the early days you can see these parameters getting much higher. And so that was the result of the 2020 paper. But in 2022, a few researchers from DeepMind, specifically, let's mention Arthur Minch, they actually had a new finding. They wanted to kind of challenge this kind of thinking. So 2 years later, they released this paper called Training Compute Optimal Large Language Models, essentially trying to challenge this idea. And their central thesis was, hey, model size and number of training tokens should actually be kind of on parity. And so when we look at, actually this should be here, when we look at what they found out, and so what are we looking at here? So in this graph here on the right, so we tried to compute the scaling law here. So we actually use 9 different quantities of compute. You can think of this as these individual colored lines. And we also chose different sized models, which you can think of as the x-axis. And then training losses, you can think kind of optimal training. And so essentially what they found out was, and you can see kind of the best place is the minimum for each one of these. That's where you want to be. And so as we move kind of towards smaller model sizes, and we look at the training loss, the TLDR is that you can draw this power law. And the power law essentially states that, like, hey, data and model size should essentially grow at the same rate, given the constraint on compute. So meaning, if I do the same napkin math, if I get a 10x increase in compute, my model parameters actually get 3 times bigger. And the same should be true for my data. If I do that again, if I do 10 times 10, essentially your model gets 10 times bigger and your data gets 10 times bigger. So pretty interesting challenge in finding in 2022. And the really cool part is this test was actually done with really small kind of models, because imagine running this would be really expensive if you ran this on very large models. So they actually tested it. Ooh, how did this get moved up here? They actually tested it in the same paper using 2 different types of large models. So they used Chinchilla versus Gopher. And the TLDR here is Chinchilla was used using the power laws you can think that DeepMind kind of found out. So the new power laws, and Gopher was kind of the older way of thinking. So we could think Chinchilla was 70 billion, Gopher was 280. And so the result was they expected Chinchilla to outperform Gopher. And the really cool thing is it was, and it did. The training set that they used for Chinchilla was 1.4 trillion tokens versus Gopher was 300 billion. So larger versus smaller. And the result was that Chinchilla outperformed Gopher on 51 out of the 57 kind of individual tasks, about 8% on average. So the really cool part is that they proved that. So we get these new power laws. Great. What does any of this have to do with Mistral and Mixtral? Well, it turns out that, wow, we did move this slide way far up. Sorry about that. So why is this important? Well, if you guys remember correctly, I think for a long time, Llama 2 was kind of like your go-to open source model. And so this was the birth of Llama 2. But for the Llama 2 researchers, they actually took it a little bit further beyond the Chinchilla scaling laws. They actually overtrained on more tokens. And so when you think about overtraining on more tokens, you think you can compress the model more. Essentially, you're trying to stuff and compress as much, you can think, training data inside of a model. And so that means it can get smaller. And when it gets smaller, that means when you run inferences, they go faster and they're essentially cheaper. And so this is why we saw the birth of like Llama 2. It was kind of everywhere. You had Llama 70B, Llama 13B, and Llama 2B. So the main thesis here is by spending more time in training, you spend less time during inference. So that compression is super key. And this concept comes important later when we talk about Mistral and Mixtral. All right, now this is the slide that, that I want. So why did we talk about any of this? Well, turns out there's 2 researchers from Llama 2 and 1 researcher from Chinchilla. So those 2 papers we talked about, they actually came together to form a new company called Mistral AI. And that's really what we're going to get into today is what were the things that they not only built off in these 2 papers, but what did they build in kind of Mistral, and how is, Mistral so kind of performant given its relatively small size. I'm going to pause here really quickly. Aparna, Aman, anything to add before we move on? Nope. Okay, great.
Nope.
So in the Mistral paper, we've kind of linked it here. If you haven't read it yet, so one really cool thing about Mistral is you can actually go and grab this model on Hugging Face. The weights are publicly available. There's 3 kind of concepts I want to go into depth on the improvements made on Mistral.
So, yeah, maybe before, just as like a summary, because I feel like, by the way, that was great of like the walkthrough of the history before we got to Mistral, right? What would you say is like there's this back and forth you're kind of explaining here of models versus compute, basically the ratio of, I guess, models to computes to data. And what's like the big takeaway, I guess? Like explain the takeaway maybe.
Yeah, the big takeaway is that there's the relationship between, so we're constrained on compute generally. We can control model size and training data, and the smarter we train our models, like during the training stage for these base models, you can think the more performant we'll get. And so the things that we actually are optimizing for in production is like inference time. So a lot of times when you're building an LLM application, you don't want to take forever to generate. You can think your tokens. If you've used you can think GPT-4, the non-turbo version versus 3.5 turbo, you'll just notice a significant difference when you get your kind of first token and the subsequent production of the rest of the tokens. So when you're building LLM applications, super important. The other thing is cost. Generally, running more parameters, so a larger model size, takes more compute to run at inference. And there's 2 costs you're optimizing for. If you're an LLM, like a researcher building models, obviously you want to reduce training costs. But if you're a user of one of these like LLM models, what you want to do is reduce inference costs. So at inference time. So generally with more parameters, you have to run more computations. And so whether you're thinking from, hey, I'm building, I'm a researcher, I'm building, brand new architectures, you're really optimizing on kind of all 3. If you're a user, what you're really optimizing for is speed of inference and then cost of inference. If you're essentially hosting your own model. I hope that makes sense.
That was great. Yeah. I think there's kind of like all of those learnings that have then come into Mistral, we're going to start diving into Mistral. But I think the takeaway of especially I don't know, I think you had on slide 7 or something of, the it's not necessarily that the napkin math that you said on the other page, like data and model set should go at the same rate. I mean, is that still true today? Is that true with the Mistral paper? Like, what's your take on this? Or has this evolved?
Yeah, that's a good tough question. I think we're always learning new things. I think there hasn't been a ton of exploration, like relative to where we are. I think 5 years from now we'll just be like, oh my God, I don't know why we did the things that we did. Um, and so, do I think we're at an optimal place today? Probably not. We can just see in 2 years we've just increased so much, and the napkin math here is, what we thought was once true is no longer true, and then we've actually gone past the Chinchilla scaling laws. And so I really do think there's a couple places we can optimize on, and it's not only like these laws or ratios between model size and training size. And we'll cover it in the Mistral paper. I think these models are getting smarter and the architectures are getting more complex, which ends up producing, I think one day we'll have very, very low latency models performing at like a GPT-7 one day. Very, very much sure about that and the investment into the research space. But I do think we're not optimized today. I think the relationship between, it's not only just the size of data. I think there's another component here, which is quality of data, completely different. So a lot of parameters here, and I don't know the answer completely.
Yeah.
Good
So
question.
scaling laws aren't everything. There's a ton of other things to go and optimize on, which was kind of against the, sort of conventional wisdom maybe for a little while.
Yeah, I view scaling laws as like the lowest hanging fruit, kind of like big jump, small change, kind of dumb small change, but kind of helped us make leaps. And so great question. So let's get into the Mistral paper. I think that's kind of what we're all here for. And there's three things I really want to highlight here. There's the first thing, which is grouped query attention, which will go into depth. But essentially, this helps us create faster inferences at inference time. The second one is the sliding window attention. It helps us not only reduce cost. Well, I think that's the main thing. It helps us reduce costs and not maybe have so many computations when we're dealing with, you can think, extremely long sequences. The last one, which is BPE or byte fallback tokenizer, it's really how to deal with like OOV or out of vocab words, so or things in different languages, and how to deal with that. That generally has given kind of large language models kind of issues in the past. And so let's go through some conceptual foundations kind of this. I'm going to go through the paper real quick, and then we can talk about some of the ideas. Actually, I'm just gonna pull this slide up. So grouped attention, grouped query attention. If you are familiar with like how regular attention works, the purpose of this kind of mechanic is to reduce computational intensity. And so you can think traditional transformer models utilize attention mechanisms to determine the important parts of, or different parts of like the input data or sentence, right? These mechanisms are pretty crucial for like a model's ability to understand or generate language, but they're known for like high computational demand. You can think like the model's trying to understand, how does this one word relate to every other single word? And so when these are dealt with in long, you can think sequences, compute can be kind of an issue. And so with group query attention, it standardizes kind of the standard approach by grouping multiple queries together. So instead of, you can think, calculating the attention for each individual token, you can think GQA like kind of computes the attention for like a group of queries simultaneously. So you can kind of think of it as like more parallelization. And what this gives us is like computational efficiency, right? While preserving accuracy. So it's one of these little cool improvements that we made that help us produce faster, better, you could think, inferences, but at the same time maintaining performance, which is, you could think, everything we're after. So that's the first mechanic I want to talk about. And so the second one, which is sliding window attention, when you think about addressing really kind of long sequence challenges, the way the sliding window kind of works is, so traditional attention mechanisms have like, you can think a quadratic kind of computational complexity, if you will. So with respect to sequence length, right? So this means that like as the sequence gets longer, the computational resources required increase kind of exponentially. So what is like sliding window attention kind of fix? So this introduces a window of a fixed size, and that moves or kind of slides across like the entire sequence. So for each token in the sequence, the model only computes attention for the tokens within that window. And this actually gives it linear complexity rather than quadratic. So you can think if you're like familiar with like big O notation, instead of like big O n squared, this is just big O n. And so why is this important? Well, obviously, it allows us to reduce complexity in terms of computation. So we go from quadratic to linear. And so something as simple as that, we're able to handle larger sequences more efficiently. Basically, tougher problems are easier to solve. And the last thing, which is BPE or byte fallback. It's kind of the way we deal with tokenization. So with traditional, you can think tokenizer limitations. It's like whether the word is like whether it's word-based or character-based, they have limitations. So word-based tokenizers struggle with OOV, or people like call it out of vocabulary words. And then we have character-based tokenizers, which can lead to like really long token sequences. And so the pros here, and I don't know the mechanics fully, but you have more like coverage, comprehensive coverage. It's like basically you have a better dictionary kind of in your LLM. It allows you to adapt kind of to different even languages or maybe domain-specific items. So you can think, oh, I'm actually answering like a very deep neurosurgical question, and there's jargon there that you wouldn't normally use. If you ever learned a new language, you're like, oh, I can speak fluently when I'm ordering food, but maybe in a business setting, I have no idea what people are saying. So it kind of helps the large language model deal with that. And so it's really an optimization between finding the middle ground between like word level and character level. So basically dealing with hard words. That's the best way I can describe it. I don't really know much about it, but if I had to describe it, it basically helps performance in terms of like weird vocabulary. And so again, I'm not explaining this like, I'm just explaining it like a layman, but if you want to go into depth, obviously the Mistral paper has a lot of this, and they talk about things like GQA, SWA, and then also the BPE. But one thing, yeah, if we want to cover one of the items here, I think it's the sliding window attention. And so just wanted to go here that the normal kind of way of doing this is vanilla attention, which it does state right here is quadratic in sequence link, and memory increases linearly. Whereas when we do a sliding window, it's you can make the computation scales up in terms of it just linearly instead of kind of looking at everything. Gonna pause. That was a lot. Go for it.
Maybe what I could do, if it's okay, I could share a little bit of, they don't actually talk about GQA much in the Mistral paper. Could share, there's another paper that talks about GQA, and there's a really good image that actually explains it. That was super helpful for me in the reading of it. Let me see if I could share over here. Okay, so this is the grouped. So like Dat was saying, there's kind of three major components that I think the Mistral paper we're going to go through. And then there's also like the gating network and then the expert tokens that kind of make up the Mistral paper. So the first big one was kind of this grouped query attention. And there's a couple different, approaches of this, essentially you could do multi-head attention, you could do group query attention, and then there's multi-query attention. And so these visuals were actually super, super helpful, helping me understand this. So the queries here, these are all kind of the blue ones over here. And essentially, in a multi-head, each query over here has its own keys, which essentially has its own values. In a grouped query, this is what Dat was explaining, where you have multiple queries that are grouped together to similar keys. And then these are actually routed to the values. In a multi-query, obviously, this is kind of, I think there's kind of a nuance here, which isn't totally clear to me in this paper as well. Is like, is grouped only limited at 2? Can it be multiple versus in a multi-query? Is there kind of spanning across kind of more than a handful or a couple that all group together into one kind of key? But But this visual is really helpful because essentially this actually helps with the speed of this, because you're not going from query to query. You're actually going from grouping a set of queries, associating with a key, and then a value. And yeah, I don't know. Any other thoughts here? I guess Dat, Aman, you guys took away from this?
Go for it, Aman.
No, I mean, I think that I don't really have many thoughts because I'm not comparing. I haven't, I have just sort of like comparing different attention sort of layers. Like this just seems like an interesting. Is this like a break? I guess my question is like, is this a breakthrough? Is this like a known method? What's unique about this grouped query method? That was my sort of question. Probably like further reading would be like, is this novel, or is this something that like, more models should be doing?
Yeah, I think it's a good question.
So this is
Go for it.
So this has actually been around. This has actually been around, like these type of different attention methods. This is actually, I think this paper was in, I don't know where this paper was in, but this paper was actually released, I guess, prior to, like, Mistral references this paper in the references. And so this has definitely been around. I think the key part, I mean, we can actually dig into some of this if we want to right now, but it says group query attention divides query heads into G groups, each of which shares a single key head and a value head. We note that an intermediate number of groups leads to an interpreted model that is higher quality than MQA, but faster than MHA, which is multi-head, as you know, represents a favorable trade-off. Going from MHA to MQA reduces H keys and value heads to single key and value head, therefore reducing the size of the key value cache and therefore amount of data that needs to be loaded by a factor of H. However, larger models generally scale the number of heads such that multi-query attention represents a more aggressive cut in both memory bandwidth and capacity. GQA lets us keep the same proportional decrease in bandwidth and capacity as the model increases. So it sounds like this was kind of a model architecture.
Yeah, kind of back
to go ahead.
Yeah.
Go ahead.
Yeah, no, just kind of back to Dat's point earlier of like, it's not just all scaling laws. Like there's a lot of optimizations you can do in various parts of your transformer architecture to try almost like get around, the sort of constraints of those scaling laws and get like improvements in your bandwidth.
Yeah, I think, so
yeah, I'm not sure if because of this, because they're also doing the sliding window, they're also doing GQA. So there's like some sort of, limitation on memory. I feel like that these models might have compared to maybe the more denser, larger models. And so I feel like there's some trade-off here, just looking at like the amount of data that's actually available for these.
Yep, I think you nailed it. I think Roshan had a question, which kind of is a perfect transition. I agree with both of y'all. I think in the beginning I think we brute forced a lot of this. Like in the beginning, we brute forced a lot of like the innovations that we saw, and we're like, okay, if we maximize the brute force, great. There's a lot of diminishing returns everywhere, and I think here we're just getting smarter in the small like mechanics, not only of like architecture mechanics, which is a good segue. So Roshan asked, what was the breakthrough of ChatGPT? Was it simply just scaling? And the funny thing is, Roshan, I think we'll cover it here. I think open source is slightly behind these proprietary models. And we're starting to get to see, we get to look into the past. I think when GPT-4 released, there were some, you can think, hints of like, hey, is there like more, is this just a bunch of GPT-3 models running behind there? And so I'm going to share my next screen and we talk about architectural changes. I think SWA, GQA, and maybe BPE are like small decisions that you can make, smaller decisions that you can make in terms of LLM architecture. But let's go through a big one. And this is dense versus mixture of experts. So what's the difference between dense and mixture of experts? Well, for the first thing is like when you think about dense, when you run Mistral 7B or a Llama 70B, all neurons participate in processing each piece of information. And so that's a pretty key importance. This is what I mean by like everything kind of works and we kind of, I want to say brute force. Dense models are generally simpler, even though they don't seem super simple relative to other things, but they are simpler when compared to mixture of experts. But there's some cons here in that they're intensive in terms of like size in terms of that. So some of the challenges here can be slow at inference time just due to sheer size. They're expensive. You can need to run at inference time, and of course to train if you're training something with almost 300 billion parameters. And that might be harder to scale. When we say scale, it might be obviously training, but obviously with inference time as well. So just note that what we're optimizing here for when we're building applications is inference speed and cost. And so yeah.
And that what is an expert network here? That seems kind of interesting as well to define that.
Yeah. So what is an expert in terms of mixture of experts?
Correct. Yeah.
That's a good question. I think Aparna can also talk about this one. There's a paper I think she mentioned in like, was it 97? Something like that. AI has been around for forever. Go ahead, Aparna.
Okay. Yeah. So mixture of experts has actually been around since like 1997 or something. There's like some paper we were trying to cover on this, I don't know, the adaptive something of mixture experts. So it's been around. It's not like mixture of experts was discovered with the Mistral paper. In fact, even the GPT-4 architecture has some mixture of experts in it. And the big one here, I mean, so with the mixture of experts, that's a mouthful to say, is there's kind of like I actually really like the image on the SMoE one. If you could just zoom in on that one, it's a good one. So essentially what happens is like there's two components here. There's a gating network and then there's experts. So the experts are basically, you think about it like they're really good at certain concepts. That's maybe the best way to describe it. And there's another paper, the SMoE paper, that talks about how like what these experts are good at is that like there's a lot of research still going in there. Like the SMoE paper, you thought, they were trying to like they observed that like experts end up specializing in a group of tokens or some sort of concepts. They thought actually the experts would be different languages, like maybe one expert might be English and one expert might be I don't know, French or Roman languages. But what they actually realized in theirs, and they actually, if you want, there's a really good image I could pull up and share it too on this one. But for me, the big thing that I was trying to figure out was like, what the heck is an expert? Like, how is an expert decided? And this is actually an image from the SMoE paper. And in this one, this is kind of the one where they were showing that there's actually experts on things like punctuation and experts on like verbs, one on like proper names. And so what an expert is, I think is, if I'm honest, I would love to know in the Mixtral paper and in the Mixtral model, like in some of their experts, like is it, how are they on specific concepts? Are they on specific, groups of tokens? Like what are the groups of tokens on? But for me, this was a little counterintuitive that it actually broke up language into these certain things. And there are some experts that were like good at certain components. And so essentially what happens is that if you go back to your image, is that given any specific token, so tokens coming from the inputs, right? That there's basically a gating network. And the gating network decides essentially which experts to route it to. I'll let that's image roll up. Okay, awesome. So if you scroll just a little bit down. Mm-hmm. Mm-hmm.
Did you want?
Sorry, okay. Oh, it's just in the image itself. Okay.
Okay. You're also
it's okay. This one's fine.
Okay.
Okay. Let me see if I can just pull up the one from the Mixtral paper, actually, to show folks.
Okay, I'll let you share.
Give me 1 second to pull this up. Okay. This is a really good image. So this is not from the Mixtral paper. This was just background material on what an MoE layer looks like. But essentially, there's kind of like this, think about it like a gating network. And the gating network essentially tells you which experts to route the tokens to. And like we were saying before, there's some experts that are good at certain types of concepts or certain types of questions. And so it routes it to certain experts. The key takeaway that's important on this is that it routes it to more. You don't want to get to a spot, and I think this is the important part of training, is that you don't want it all to go to one expert. Like, you don't want it to be highly specialized with one expert. Every single time it's just going to the same expert. There's actually as part of the training of the Mixtral paper, one of the things they talk about is like there's some kind of loss where they essentially are optimizing over, so that you have the spread of tokens. It goes out to as many of the experts as it possibly can. So there's some kind of like even load distribution across the experts. And part of this is also for each token, how many experts can you call on? So can you call on, I think in this one and then the OpenAI GPT-4 paper, they both had 2 experts that it called on. And so there's some minimum where it doesn't just go to one, but it actually goes to multiple experts per token. But this is actually, I mean, this is just outside of even the Mixtral paper. This is probably some of the key takeaways on just like how do mixture of experts even work. There's typically a gating, it passes into the experts. You want to optimize so that there's load distribution on your experts. And then you also want to optimize so that you have multiple experts being able to be called on for each token. And maybe we'll get into this as we go into like the fine tuning components, but this is also why one of the reasons why it's really hard to fine tune mixture of experts types of models.
And there was a note there on mixture of experts, like kind of optimization, that's a really great, we'll drop the blog post as well, which is that you're referencing in terms of there's a ton of optimization. There's like switch routing that they mentioned. So that whole layer sounds like, it's almost like you are literally fine tuning that layer to perform, an even better sort of, task at switching between experts. So that was pretty interesting as well. It's like a model within a model.
Yep, nailed it.
Yeah, and there's some point where past this, it's like, how many experts do you want? Like, do you get to a point where the number of, I think they actually did some analysis of like, do you add more experts? And you do see kind of like improved, you do see improved performance, you see efficacy in like which experts to call on, but there's some point where there's just diminishing gains of this. And so I think this is also an area of where, that looks like you're about to get into it with switch transformers. But I think this is also an area of like, where does the diminishing gains happen and how many is really enough? And is this an area where in the future of MOEs, we're going to see more and more? Do you try to optimize the number of experts?
Yep.
Keep going, Dat.
Yep, that makes total sense. I think there's a lot we're still learning too. I think we'll definitely go over switch transformers and what they optimize for there. But for those folks who see MOE, yeah, it consists of, so the difference between that and a dense network is like not all neurons fire, and we'll definitely get into the math of like how these things fire off. And what are the gains we get from MOE? One, you can think specialized workers that don't always fire, which is great. You can think of it as like, hey, I have a specialized team. And just one heads up, each token has its own path and experts. So there's not like, hey, I'm sending in a paragraph and this paragraph just sends in like to these 2 experts. It's each token gets its own. So it starts to make a lot of sense when Aparna showed kind of this is at the language level and at the token level. So super important to denote that. But the MOE architecture allows for like an overall increased number of parameters. When you think of, if I add up all the experts and the non-feed forward neurons, you have more parameters, so basically more capability. But since you're not running it through everything, you reduce things like inference time. You reduce things like cost for the same or better performance, which is kind of everything we're looking for. And so major architectural difference change. And so knowing this, maybe like in the past when we saw GPT-4, that might have been OpenAI's this like, transition over into MoE. And like Aparna said and Aman said, there are challenges here. Knowing how to train MoE architectures is actually more tricky. There's actually a lot more math involved, as you can imagine, because of more complex architecture. But there's also proficiency knowledge you need in optimizing hardware use and just overall more rigor. And there's also constraints around, you can think, managing tokens and routing. So it comes with its own kind of set of kind of challenges. And so, like I said, each token has its own path and set of experts. And like Aparna said, I won't cover this in depth, but a gating network or router kind of determines which tokens are sent to what expert. We can kind of look at here that, like, when we look at the token more versus the token parameters, they can kind of get sent into different routes, you can think. So hence the router. And so your question should be like, okay, how does a token know which expert to go into? So what are the things that affect that? Yep.
I could share a little math if it's helpful, just to think about this one. I think the math always helps me understand this. I want to share real fast stat on this one. Okay, let me go back to this. By the way, yeah, I think Sarah linked it and Amon linked it, but this blog post by Hugging Face was actually freaking awesome. It's just explaining kind of a lot of what we're covering today. But essentially, this is essentially what we're saying here, which is like, okay, how do you know what tokens end up at what expert? And, there's a lot of things to caveat here, because if you have uneven distribution or some experts don't get utilized, there's, that's kind of what you don't want. And so if you just think about it in like a really simple format, this was great to help me understand this. So there's a gating network, and then there's a number of experts. In the beginning, if I just thought about it as like, what I want is, at the end of this, is to know which experts should the tokens go to. And you could do is think about the gating function as like, if the gating function is 0, which will be for many of the experts, then it won't need to go through the compute for all of those respective expert operations, and hence we save the compute. And so in this example here, they just did something like, I think just to explain it, like a simple softmax. But post this, so this is kind of the gating function, the experts itself. So there we go. So this is actually where they're doing the top K, and the top K is because we don't want it to be just a single, just a single one here. They want it to actually be more than one expert, so the gate learns how to route to different experts. So at least 2 experts had to be picked. I think the switch transformer paper kind of, like I said, revisits this. But if you think about it, essentially this gating network function here is essentially, it's like weighted multiplication. It's helping you figure out at the end of the day which expert to pass it through. Most of them will be 0, which means it only has to go through compute for a specific set of those experts. Hopefully that was helpful to give a little math there.
Yep, sure was. Okay, I think we're kind of coming up on time, so definitely want to just cover Mixtral 8x7B. So I actually find the name a bit misleading. When you actually do the math on this, so just as a heads up, not all 7 billion parameters are being 8x'd. So 7 times 8 would be 56 billion. But when you look at the total number of parameters in the MoE, it's actually 46.7. And then your question is, okay, why? Like I said, not everything is duplicated 8 times. Actually, there's a certain set of non-feed forward neurons that just fire every single time. And so if we use a system of equations and we think, hey, in the total model, we have 46.7 billion parameters, and there's 8 experts. If we just fire one token, right, and we see how many parameters are fired, it's 12.9. And so using a system of equations, we can actually just understand that the number of parameters per expert is around 5.6. The non-feed forward blocks are about 1.6. And then if you add that together, that equals about 7.26. And so just really interestingly enough, only 2 out of the 8 experts are ever executed for a token. And so when we think about MoE and why is it helpful and what kind of happens here, I'm running significantly less number of parameters, but have significantly more access to more parameters, if that makes sense. So each individual token essentially gets the parameters or you can think experts that it needs to make better, you can think generations. And so that router mechanism, which Aparna covered in depth, super important. All the papers are linked, but just wanted to quickly show kind of the model architecture here, and really how did this thing perform. And so the Mistral paper, they tested this against, Llama 17, 7, 13, 34 to 70B. Sorry, not 34, just 7, 13, and 70. We can actually see the results. And so MMLU is massive multitask. Let me double check that. Yeah, MMLU stands for actually massive multitask language understanding. And so this is kind of the main metric used, and we'll go over it later, but we can also see some interesting things too in other places: knowledge, reasoning, comprehension, math, and code. If you notice the one area that Mistral and Mixtral, or specifically Mistral, doesn't perform super well, it's knowledge, right? And then it starts to make a lot of sense why. Because when you think about it, knowledge, or like what knowledge is contained inside of, you can think an LLM, generally constrained by parameters, right? Even though we're compressing better, we have significantly less, you can think, parameters to store or compress that knowledge in. So the really cool thing is this makes a lot of sense, because when you think about knowledge and compressing the model, Mistral 7B tends to outperform Llama 13 in almost all cases, except for knowledge. And the constraint here is the parameters, because you can only compress so much, right? So really interesting thing here. One interesting to highlight is Mixtral, so the MoE model, is about 6 times faster than Llama 270B. And then performance, you can just see it just outright just outperforms everything here. And then anything else to add, Aman, Aparna, before we?
Yeah.
Yeah.
Yes, in the interest of time, just seeing we're a couple of minutes over. There's a lot I feel like we still haven't even gotten through on this, which is like the evaluation results, limitations of these models on things like fine tuning, etc. I feel like there's just a whole deep dive we could still even do on the architecture of it. So why don't we do this? Let's the next community paper reading, we'll just keep deep diving in on Mistral and Mixtral. And let's follow up on this. There's just so much we have still yet to cover on this. Let's do it. Hope you all enjoyed this. I know it was a lot of depth in this one, but hope it was fun to just hop on and talk through the paper. Cool. Thanks, everyone.
Awesome. Thanks.
See ya.
Thanks, y'all.